Good afternoon, everyone. My name is Kashim Sanni from Polytechnic Montreal. Today, I will be presenting to you a recently developed alloy codenamed M789 Martensitic stainless steel, basically. A brief outline. First, we go through the context, a little literature review, methodology and results, which leads us to some conclusions. Okay, our industrial partners are basically concerned with the production of plastic corks. These corks are actually produced using continuous compression molding machines. These machines are quite in use with what we call the die inserts. These die inserts are made from high chromium martensitic stainless steels. Nonetheless, because of the internal channels that we have that often pulls the machine or the inserts when they work, the need arises that they must be very tolerant to fatigue or discontinuities, largely because we're operating at 2,000 cycles per minute. So the industrial partners are experiencing the challenge of fatigue failures and the incidence of corrosion as well, because the internal cooling channels have some fluids that create a corrosive environment. To that effect, they decide to leverage upon the an additively manufactured alloy, largely because of the benefits of AM, i.e. complex parts, as well as the tendency for the material in question to have good corrosion resistance property, i.e. in the aspect of pitting. That is what led to the intent of using a new alloy called M789. The alloy basically is a precipitation hardened martensitic stainless steel. What is just important here is it has martensite. This martensite is optimized basically from an age hardening heat treatment after solution annealing. Consequently, we have optimized properties and strength as high as greater than 1,600 MPa. And recently, we have a publication that found the delta K threshold to be about 4.42 at 0.1 R. As expected, you can't have AM without discontinuities, and typical ones and the material are non-metallic inclusions, lack of fusion roughness, and with our recent experiment, we also noticed that it has susceptibility to pit. Inevitably, you have discontinuities, you have an environment that will have fatigue. The next thing is we go with how do you correlate the fatigue damage mechanism alongside the discontinuities. We go back to the evergreen Kitagawa-Takahashi diagram. Previous colleagues have spoken about this immensely. I wouldn't want to talk much about it anymore. But what is important is the Kitagawa-Takahashi diagram is often pegged as non-conservative, and lots of models have been advanced to improve the conservativeness. Typical amongst them is the L-Haddad. The L-Haddad basically modifying the LDFM part of the curve to give a smooth transition for the data that in tandem with experimental data. Also, Murakami and Endo have advanced another model as well that is dependent on the material property of hardness along with the size of discontinuity. And it defines also that region, as you can see. Basically, it's just trying to improve the conservativeness of the data. For a first start, since we are at the preliminary phase of the research work, we intend to see which of these models are more predictive of or are more in tandem with the experimental results, so that we can now from there proceed with optimizing them. Hence, we intend to predict and compare the fatigue strength of the alloy using the models as I've given. Also, we also intend to see which of the failure mechanisms might be occurring other than the fatigue, or sorry, the discontinuity influence, and which of these discontinuities is more critical to the fatigue strength. Methodology. Like I mentioned, we do not have an idea of the material in itself, i.e. the fatigue strength. It becomes imperative that we carry out an axial fatigue test. Nonetheless, we intend to patronize the step loading technique proposed by Locati method and recently modified for simplified calculations by Maxwell and Nicholas. Basically, it's a stepwise increase of the load till failure, then you compute a linearized version of the strength, fatigue strength. For you to effectively carry this out, what you need is a prior knowledge of the fatigue strength, which we do not have at our disposal. The best solution we could resort to was to find an ability to predict the fatigue strength that will give us an idea where to start the strengths from. That is one. Secondly, so basically to do that, we want to use the extreme value analysis. The second advantage of that is just for our industrial partners, sometimes when you manufacture products, you want to also have an idea of the fatigue strength of the material. Basically, since you know it has discontinuity, if you have a given volume, you want to be able to predict what the approximate fatigue strength will be. So it's a twofold advantage we try to leverage upon in this regard. The EVA basically utilizes a small field of view. This could be a metallographic specimen in which you subdivide them into blocks. These blocks, we collate them block maximas, and we plot it onto a linearized version of the Gumbel distribution. Typically, that will follow a straight line, and we can do a linear regression to get the equation that describes that line. Nonetheless, if we are interested in predicting the fatigue strength for a higher specimen, in this instance, fatigue specimens, what we need is a return period in relation to the small size field of view. That return period and the characteristic equation, we predict the fatigue strength to that point, and superimpose it on the square root area there, and that tells us the predicted fatigue strength if it's a fatigue specimen or even if it's a larger block size specimen. Nonetheless, this is the size of the discontinuity expected in the fatigue specimen. So what we do, we have models that predict fatigue strength based on size of discontinuity. We superimpose it on fatigue strength prediction model. This FS prediction model could be Murakami or El Haddad. So this is a schematic representation nonetheless. As such, the point of intersection there is the fatigue strength and the square root area to failure, expectedly, like I said, theoretical. These are all theoretical predictions. So with this, we have an idea that, okay, for economic purposes, for time saving, where to start our experiment from. Another step we decided to do was to expose the prior Ohinoyi grain boundaries. It's a Martensitic stainless steel. So the challenge is most times these steels are basically Martensitic, and you cannot have an idea of the parent Ohinoyi grain boundaries. The fact that we don't have any prior knowledge of this material led us to unveil the PAGB. What this portrays is that the PAGB, the Martensitic hierarchical structures, can all be influential depending on the material behavior. We do not have this information at hand. We know the martensite lat size, and with this, we were able to get the parent Ohinoyi grain size basically optimized between 15 to 35 microns. Nonetheless, in terms of fatigue, we are interested in the extremities. The extremities are more influential, i.e. the large parent Ohinoyi grain size. So now we have a material parent Ohinoyi grain size, and we also have predictions from the fatigue strength. We performed our fatigue test, and we now see what the fractographic results are, first of all. This is one of the specimens that failed. Basically, we have the failure origin, the crack initiation origin, and it failed from a non-metallic discontinuity, which is more of an alumina. Another specimen, all these specimens are polished specimens. This also had a crack initiation origin that failed from a lack of fusion discontinuity, typical of additive manufacturing materials. And for this specimen is an as-printed specimen. Interestingly, the failure mechanism is quite different from that of the polished specimen. We had dual crack initiation sites, a primary one that drove the failure and a secondary one that was quite side located. What we see is, firstly, there isn't any discontinuity at the failure origin. What you have is a failure that's inspired by the surface heterogeneities, since it is in the as-printed condition. What we can also say is we can see that it is evident that crack has initiated from different local spots, largely on planes that are crystallographically aligned for fatigue crack initiation. Obviously, they obviously grow to coalesce and propagate on a single plane as described by those lines. We could also see some microstructural features close to the failure origin, which also signifies the incidence of crystallographic failures. If you look at the secondary crack initiation sites, we also had another feature there. That feature, EDS analysis showed it has the same base chemical composition as the material, so it wasn't an inclusion. Comparing that size to the PAGB frequency distribution that we previously showed, we can superimpose and we see that it falls within the parent Ohinoyi grain size. This is a pointer that probably we could have microstructural influence and some competition ensuing. Hence, we thought to superimpose the result of discontinuities we've measured at the failure origin alongside the parent Ohinoyi grain boundaries measurements. And we could see that these discontinuities actually fall within the large grain size. The consequence of this is the possible competition for fatigue crack initiation between discontinuities and microstructural contribution. This is especially severe when we come to the as-printed specimens. So for this particular material, our initial phase of conclusion for here is the microstructure might just be having some contribution to the fatigue failure process. We have the cleavage failure, or that is typically would have expected failures to come from discontinuity, but we're also seeing the microstructural contribution as triggered from the heterogeneous surface. And this is just to superimpose further to really see where these discontinuities lie within the parent austenite grain size. Okay, now we did some extreme value predictions. We have our fatigue test that has been performed, and we have the size of discontinuities. We first of all have to see how the extreme value predictions correlate with our experimental data. Like I mentioned, it will give the advantage of how reliable it might be in future, just in case our industrial partners intend to predict the fatigue strength of their material as well, based on a larger size component. More so, we want to see these discontinuities, which of them also conform to the Kitagawa-Takahashi diagram or the models as previously highlighted. Now, this is the prediction of the extreme value. So these are theoretical predictions from metallographic surface. Here we've superimposed the large size discontinuity on both models of Murakami and El-Haddad. And we have those predictions of the fatigue strength, 384 over 365. Murakami model is quite over predicting the fatigue strength, while El-Haddad is a little bit more conservative. That is intuitive anyway, if you follow the Kitagawa-Takahashi diagram. The theoretical prediction as well for the printed specimen is virtually the same conformance. Murakami overestimates, El-Haddad is more conservative as regards to the Murakami model. These indications here, these bounds here, as well as the previous bounds, will be superimposed on the Kitagawa-Takahashi diagram alongside our measured discontinuities at failure. So firstly, we have the Kitagawa-Takahashi diagram, we have the El-Haddad model, and we have Murakami as well. What is quite evident is most of the data points fall on the predictions of El-Haddad in the long crack region, along with the Kitagawa-Takahashi diagram. So the first thing we can say is the Kitagawa is non-conservative. In fact, it's not even applicable in this regard. And El-Haddad could be more patronized. Secondly, we have it that the predictions of extreme value should be taken with caution. In this instance, we can see that the extreme value predictions may just somewhat be underestimating the fatigue strength. Similar with the aspirated condition, they just might be giving predictions that might not be reliable. Hence, it should be taken with a pinch of salt if you do them for prediction. Okay, that brings me to the conclusions of this experiment. The Murakami is a lot more non-conservative. Subsurface discontinuities were influential on the failure, and we have the microstructural influences that seems to be emanating as well. Extreme value estimates should be implemented with caution. Our next phase of the research work will be centered around the the generation of discontinuities, i.e., what I'll call secondary discontinuities or environmentally influenced discontinuities, basically electrochemical pits, which we intend to pit specimens to produce electrochemical pits so that we test them and we see the competition that is ensuing. Like you remember, I said the specimen for which this, the component for which this material is meant for actually operates in an electrochemical environment. So the potential or the propensity for pits to generate is quite existential. Thus, we are also going to generate pits, which are currently ongoing, to see how they also compete with the additively manufactured discontinuities that are naturally occurring in them. Also, we intend to manufacture specimens with internal cooling channels. This will mimic the component in service. Like I mentioned, the component has internal channels for cooling as well. Doing that, we are able to now have an idea of which of these discontinuities we have additively manufactured discontinuities naturally existing, environmentally influenced discontinuities, design influenced discontinuities as per the internal cooling channels. From there, we see the competitions as regards crack initiations. And that brings me to the end of the presentation. Thank you very much. I have my references here, Polytechnic Montreal, my number, my email.